Okay, if we pick up from yesterday, then the remaining part of this handout has got 4 different reaction mechanisms on there. We're not going to use all of these, but if we just sort of have a quick skim through them so that you know what they're there for. The first one, you've got homolytic substitution. Now, homolytic means equal splitting, remember. So homolytic substitution and the one that's described here, a free radical photochemical chain reaction. That is the one that we're going to look at. So this is an important one, but I'm not going to explain through it here. I'm going to do it separately. The homolytic bit means that it starts with the equal splitting of a chlorine molecule. All right, so the starting point for this is our chlorine becoming, it becomes 2 chlorine radicals, and the way we actually write a radical, although this is going to come back to us, we get 2 of these. All right, not just, we don't just put chlorine like that. You put a dot after it. Now it's to show that unpaired electron, and it's halfway up the letter or down the letter, depending on how you look at it. And I'm not sure if it's possible to find that as a symbol. It must be, I think. But yes, if you decide to type any of the mechanism out yourself, you'll have to find a way of putting a dot to represent radicals. So that homolytic splitting there means that each of the 2 chlorines gets one of the electrons that was in the shared pair. It's equal splitting. And the substitution is hydrogen atoms in the molecule being substituted by the chlorine. The molecule that we're going to start with is our, well, it's going to be an alkane. So it's the hydrogen in an alkane replaced by, in this case it's going to be chlorine, but it could be anything else, all right? But if you have a look at what that mechanism shows in those diagrams, and it does look complex, but you've got the 3 diagrams there. Stage 1, initiation, is producing free radicals. Stage 2, propagation, you get this chain reaction, and I'm going to explain through that. And then stage 3, where the free radicals actually join together to produce the substituted molecule. So overall, yes, we end up, if we started with methane, we'd remove one of the hydrogens and end up with chloromethane, all right, which would be 3 hydrogens on there, but 1 chlorine, all right, rather than a 4th hydrogen. Now, if you've looked carefully at your assignment, you will realise that you're only being asked to do exactly the same thing, but using bromine instead of chlorine. All right, so it's not exactly challenging, but it's about your explanations and whether you take it as far as you can. All right, so once we've done this, then you know the only thing that you've got to change is to change the chlorine into bromine. So that one we do need, all right, so that's in the assignment. The second one that you've got on that page, homolytic addition. Now, homolytic addition we're not doing in the assignment, but again, this idea of homolytic means equal splitting again. But this one is a free radical polymerization reaction. Again, you have initiation, which is about production of free radicals. I'm not going to explain through this one at all. You get a chain reaction there. I'm just trying to work out if I know what that is, and I don't. All right. So not needed, that one. But the production of the free radicals means that you've then got reactive components that can actually join together to create a polymer being a repeating chain, a chain of repeating units, I should say. All right, so we've met two polymers already this morning in biology, and that was our polysaccharides, the chains of sugars. Those are polymers, polysaccharide, polymer. Right, the sugars are the units that build it up, and also the protein. You know, so where we'd got, what was it, 400 and can't remember how many amino acids in that D antigen. The D antigen is a protein. It's a polymer. All right, so polymers just repeating units. And so you can have a homolytic addition process if you create free radicals that will then react with each other. Not going into that one. Over the page, heterolytic electrophilic substitution. We're not doing that one either. Heterolytic is where you get the unequal split of your starting molecule. So you might well be producing free radicals, but yeah, it's not through an equal split. And so heterolytic electrophilic, so this is about having a reactant that will actually pull electrons away. Substitution, again, it means replacing one component with something else. And here, this uses the benzene ring that we've got there. That hexagon with the circle in it is the benzene ring that I drew yesterday to show the way the electrons are positioned in that pi system. And that is actually pretty much what we'd got yesterday, that the electrons in the pi system of the benzene are drawn towards an electrophile. We've then got a slightly more complex reaction process going on there. I'm not going to try and explain it because we're not doing this one. So it's just there to sort of, add examples. Okay. There are some others as well that we could add to this lot, but, we've only got so much time. The fourth one on the sheet, however, we do need heterolytic electrophilic addition. So this is one that comes up on the assignment. Heterolytic, again, unequal split. And we did actually look at this yesterday. This was on I think this is the one. Yeah, no, it's not that one, is it? This is just using bromine. The one that was on the curly arrows sheet, which was where people started losing the will to live. It was hydrogen bromide, right? But that the electrons moved unequally. In the hydrogen bromide, we had the whole pair move to the bromine. So that's why it was heterolytic. So that was an unequal sharing of electrons. Electrophilic, so this one is going to be, trying to remember what's in the assignment on this one, but the example that you've got is very similar to the one that I'm going to go through. Hydrogen bromide, okay? So that's the one on the curly arrows sheet. Yeah, yes, I don't know which one's on the other sheet I'm giving this afternoon. So the heterolytic bit just means unequal, unequal split of bonding electrons. And what that's generally going to mean is that one of the bonding atoms is going to get both of them, the other gets neither. Yeah, so what you got on that sheet yesterday, the hydrogen bromide, the bonding pair went to the bromine, leaving the hydrogen without one at all, so the hydrogen actually just became a proton, but that was then bonding to the rest of the molecule using the pair from the pi bond. Yeah. So this one, we're going to need that one. And the stages here, again, you've got the three stages. The initial attack, and this is where the pi electrons become important. And your stage two, a nucleophilic attack on the intermediate. Because it's already very well saying electrophilic, but when you are looking at electrons, you've got some in one place, but you haven't got them in another place. So you've got to have both situations: too many electrons, not enough electrons. So you will always get, you know, a certain sort of tendency to one of the terms rather than the other. And then we get, yeah, that's made it a fairly complex description: production of trans-addition product. I think that one, you know, is perhaps less useful as an illustration, but the notes I'm going to give you from ChemGuide will be extremely useful, shall we say. And one thing I would say about this assignment is you could pretty much just copy and paste off ChemGuide. Don't. Right? It does need to be in your own words. You could copy and paste images, perhaps, if you felt they were useful. But if you can find other ones, if you can draw them yourself using the drawing programs, great, but that is quite difficult. Okay, let's have a look at our two mechanisms then that come up in the assignment, and then I can let you get on with it. The first one, free radical substitution. Okay, so this is just our first example. So I realise there will be a gap in the recording as I give out handouts. Oh, didn't I give you enough? The trouble is the staples stick to each other. Right. Okay, back to the board. Now what I've given you there is, it is literally just copy and pasted from ChemGuide, because it's so well explained on there. And there's no point in me reinventing the wheel, as they say, you know, rewriting it in my own words. You know, I mean, Jim Clark's got, I don't know how many years experience as an A-level chemistry teacher, so, you know, this is good. I have put, there are two parts on here. For some reason it printed single-sided, which annoyed me. You've got, to start with, just a little bit about substitution reactions. And then over the page, you've got the reaction between methane and chlorine, right? But what you've got, methane and bromine, will be exactly the same. And I suspect that's on there anyway, right? I think he's got the bromine reaction on the site. This does not go as far as it can, all right? So I will, you know, flag up what that means in a minute. And then at the end, I just stuck another sheet on to show just some of the other ways that you can represent some of the processes that are going on here. I think the lower box there with all its little fish hooks on it is particularly useful. You know, you need to get your head around the idea of where these electrons are going. Okay, to start with then, this idea of substitution, a substitution reaction, it is what it says. It does just mean replacing one atom or more with a different one. You know, there's nothing magical to it. It's not a specific chemistry word. It literally does just mean a substitution. And so he goes through, you know, some examples here, and the important thing really is that, and he will always do this, say at A level you only need this. So you have to realise, you know, if you do go beyond this level, then you might you might need other types of substitution reaction. But it's the general principle is about replacing one atom with others. So the examples he's put there, you know, it's usually about, well, at A level, it's about breaking carbon-hydrogen bonds in alkanes such as, so you've got methane, ethane, propane. So breaking a bond between a carbon and hydrogen, and then forming a bond between the carbon and something else. He's just said with a new bond is then formed to something else, but it's the bond between the carbon and the hydrogen. that you break, and then the hydrogen goes away and the carbon bonds to something else. It then goes on to say it happens in alkyl groups like methyl, ethyl. Well, that to me is fairly obvious, but you know, it's, as long as you're breaking a carbon-hydrogen bond and replacing the hydrogen, it doesn't really matter where. So that's the first thing to understand, the idea of a substitution reaction generally. And then the idea of free radicals. Now, we have met these. You know, yesterday we met the idea of the free radical. And the one that we met was the chlorine free radical. So just a recap, although no, we're going to come across it over and over again, that if we've got a pair of chlorine atoms bonded together covalently, oh, I can't remember which way up that had to go, with our, using the Lewis structure, it's always convenient for that, the break, right, I'm going to have to do it through there now, is such that you get each of the chlorines getting one of the electrons out of the bond. So this then becomes a free radical, and we write it like that. That dot is showing its unpaired electron. Here's the other one, exactly the same. And while, as I say, they are essentially just atoms, the you know, the important point here is an unpaired electron. All right, makes it a very reactive thing. The word thing I could replace, actually. I don't like to use the word thing. In chemistry, and it's odd because it's a word that we associate with biology. If you're talking about any sort of particle, it could be an atom, it could be a molecule, it could be an ion, it could be a free radical, it could be anything like that. We very often just use the word species. All right, now, you know, a species in biology identifies a very specific group of living organisms. So I could say, you know, that these are very reactive species. All right, it's a useful word, but if you come across it, that's all it means. It doesn't mean atom, it doesn't mean molecule, it doesn't mean ion, it doesn't mean free radical. It just means whatever it is you're talking about. It's easier than saying particle or thing. All right, thing is not a good word in any subject. So this idea of producing free radicals, in this case by homolytic fission, or homolytics, you know, separation of the bond into the two electrons that end up, you know, one to each of the chlorine atoms there. And as I say, these dots, these halfway dots, yeah, we'll have to have a look at Word, and it'll be insert symbol, and you will find somewhere there'll be a dot there if you need to do it. It's not just a molecule like this, though. We can also create other sorts of radicals, and the one that we're going to need for this particular reaction is a methyl radical. Now, the methyl radical is produced in the same way. Just thinking whether we actually have the diagram coming up anyway for this. Sorry, just bear with me a minute. I don't want to do things that I don't want to repeat myself too often with this. Yeah, our methyl radical. It's curious. If these are chlorine radicals, the methyl radical with its odd electron is usually written like that. But in fact, the unpaired electron does belong to the carbon. All right, so that's a methyl radical. Methyl, because you know, it's just got the single carbon, that will originate from the methane. All right, methane, CH4. If you break the bond between the carbon and the fourth hydrogen, then you actually give the electron, well, give one of the electrons to the carbon, one to the hydrogen. The hydrogen then goes off and actually will react with the chlorine. But the one that's left on the methyl radical actually is the unpaired electron for the carbon. But it's usually written like that. It's usually just kept as a group with the unpaired electron put on the right-hand side. If you were going to write it accurately, I think he mentions this actually in his little note underneath, you'd actually write it like that. And that would actually make more sense. You'd sort of understand that the carbon had got this unpaired electron. And I don't know that it's wrong to do that. You know, you could write it like that. But he says, yeah, this isn't normally done unless the radical gets more complicated. So, yeah. All right, so the methyl radical that we're going to meet will be written like that. Now, let's have a look then at this actual reaction between methane and chlorine. It's a separate page off ChemGuide, and it's the first of two, and I haven't put the second one in. All right, there's a reason for that. All right, now this first page looks at the substitution of one of the hydrogens in methane with a chlorine atom. Now, that's not necessarily where it stops, because you can continue and replace the second one and the third one and the fourth one. All right, but this just starts with that substitution reaction, just replacing one of the hydrogens with a chlorine. The second page does the complete thing, I think. But, you know, that if you're looking for better grades, then completing the whole reaction is worth considering. Right, so reaction between methane and chlorine. Now, if we happen to have some chlorine gas, which we haven't, you can put chlorine and methane together, put a light to it, and you get a fairly significant explosion. Not doing that. But this can actually be done in it's a much more controlled sort of way that you can carry out this substitution reaction. But it can be driven just by light energy. All right. So somewhere in this it will tell you about this. Yeah. So if you mix methane and chlorine, put a flame in, it explodes. Yeah. Okay. But the version that we're looking at is not that. That we're actually looking at what we would call a photochemical reaction. And so it needs, it uses UV light. I shouldn't put light, really, should I? It's just UV radiation to actually get it going. Right? So the UV radiation is going to be our starting point, and that can just be sunlight, or it can be in sunlight, I should say. And the first step, right, now the way that this works is that we have the overall reaction. You'll find that at the top of the page. Overall, what we're looking at, if we just substitute one hydrogen, is that our methane plus chlorine, well, we lose a hydrogen off here, we replace it with a chlorine from there, so we get that, right, chloromethane, or you could call it methyl chloride if you wanted to, but chloromethane is more accurate. And then you're left with the hydrogen that came off here and the chlorine that didn't react. Yep, so we get HCl, hydrogen chloride. So that would be our overall reaction. But as I say, you could then take the CH3Cl, react that with chlorine, and again, then, well, you'll get CH2, Cl2, and HCl. And then if you put the CH2, Cl2 in with more chlorine, you'll get CHCl3 and hydrogen chloride. And if you take the CHCl3 and more chlorine, you end up with CCl4. All right, tetrachloromethane. All right, which used to be called carbon tetrachloride. It's a dry cleaning fluid, carbon tetrachloride. Nasty. So you can just, progress until all the hydrogens have been replaced or substituted, I suppose I should say. But there's stages that this happens. That doesn't show us the mechanism at all. So the mechanism is now what we need to do. And I think I've probably got to stick on this one page now. You've got so many diagrams of this. You've got it within the written bit off ChemGuide, and then you've also got those two sets of diagrams at the back as well. And you will, I think, probably need to use the more detailed page off ChemGuide, or anywhere else. You don't have to use ChemGuide. You know, I should give an extra grade for anybody who uses another site, shouldn't I? We have the 3 steps have very distinct names. So we have initiation, propagation, and termination. And it's all to do with this chain reaction. So the chain initiation so this is our first step. The chain initiation is simply just the production of the chlorine radicals. All right. Now, if we were going to put the curly arrows in this, then, well, we're not going to. But this is, we did it yesterday, but we did with this one, sorry, going back up here, we did the, yeah, I did the fish hooks, didn't I, showing that those were, whoops, nearly did a double-headed arrow, showing that they ended up back towards one side. But this is where our UV light is, well, all right, UV light, zip, zap, 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 zap. Here's our chlorine. And we get 2 fluorine radicals. Right. So that's a very strange looking arrow there. But the energy from the UV is sufficient to break the chlorine molecule apart. And once we've got our chlorine radicals, we can then, because we've got something, a species that's really reactive, we can then actually rely on them to get everything else going. So once the chlorine has been split apart by the UV radiation, then the rest is this chain reaction process where those will trigger the next bit, they'll trigger the next bit, and so on. So once we've got our chlorine radicals, our chain propagation, propagation sort of means growing or something like that, if you like. Propagation, it continues the chain. And we've got 2 things that happen here. The first thing is that our chlorine radicals might possibly bump into some methane. Now, if they do, then the chlorine radical, all right, with its little electron there, is going to... do I put the curly arrows in? No, I'm not. I think if I put the curly arrows in, I'm almost doing the assignment for you. But you can see it on the sheets. I'm probably going to, aren't I? Yeah, but you've got them. This is the thing. The chlorine radical then bumps into methane molecules, and what we end up with as a result of that is the production of our methyl radical, right, and some hydrogen chloride. Now, you've got a diagram of this that shows where the electrons are going, but I can't stop myself doing it, actually. I'm going to have to do it probably the other way round. Yeah, if we will use the one that's on the sheet. I'm not going to generate my own and make a mess of it. There's our methane. Doesn't go with the diagram above, does it? And our chlorine with its odd electron. And what's happening here is that we've got a pair of electrons here, remember. One of those pair, right, I'm going to draw them in, although, you know, shouldn't really. One of them is drawn back to the carbon. The other one is then drawn between the hydrogen and the chlorine. And, I don't know which way round would have been better, actually. Sorry, I'm going to redraw this. You can tell this is not something I do every day. I'm actually going to leave it like that, because that, to me, actually puts an electron in a better place. So, yeah, sorry if you were using that. Right, let's do it this way. One of those electrons then goes back to form our methyl radical. We'll have this odd unpaired electron. Then, what's rather good about drawing it this way round is that that goes in there, that goes in there. That's better. That's a far better way of drawing it. All right, there is a plus there. And so the odd electron that's being carried by the chlorine joins with one of the electrons that was in that bond there. All right, so one electron moves there from that bond, the odd one moves there, and these two can now form the bond in hydrogen chloride. Okay, so that and that form the bond between those. Okay, so, all right. What, between those? Yeah, should do, because it is a reaction that's going on. No, not really. No, it's just whatever you can fit in to make it tidy. Because the plus isn't a thing. It's really just showing that this and this together will create that. All right, so, you know, I could, I suppose, complete this, couldn't I? So we've got our HCl there, and then the CH3. You can see that, you know, I've taken the odd one from this side, so that's a situation where I would be inclined to put it there, but it doesn't matter. You can put it on the right side or the left. It, you know, doesn't matter at all. So that's all the same step. All right. No, just one of them. And the curly arrow bit is what I actually want to see. I want to see you using curly arrows and fish hooks all over the place. So that was really just a summary of what happens, and this is actually showing where the electrons move. So that reaction occurs because of that. What?
On the other sheet they call it cleavage.
Oh right. Oh yeah. Yep. Cleavage is good. Cleavage just means split, doesn't it? So yeah. We can that's a good word. The other thing that happens in the propagation process is that you've still got chlorine molecules lurking around. They didn't all just get split into free radicals. But because we've now created some rather reactive methyl radicals, these CH3s, and I'll do it the simple way first. And I just realised that the top box on that sheet, that last sheet, just has CH3. It doesn't have a dot. All right, there's no radical dot there, and there should be. The one below is okay because you can see where it's going with that one. But that will collide with chlorine molecules, and what do you know? You get a reaction that produces our other end product, the CH3Cl, but in doing so, it's generated another chlorine radical. Yes, yeah. So we've got another chlorine radical produced by that. So you can see how this is now keeping itself going, because those chlorine radicals can then bump into more methane and produce more methyl radicals that can bump into more chlorine and produce more chloride radicals. Hence, it's a chain reaction. Yeah. So you can see on the handout sheet, you've got the curly arrow or the fishhook version of that. I'm not going to draw it up here as well, because you can look at that sheet and do your own version of it. But you've got in the lower box on that last sheet, you've got the good curly arrow or fishhook version. You've got the odd unpaired electron here from the methyl radical, this one, okay, is moving to a place between the methyl radical and the chlorine. One of the electrons from the chlorine molecule is going to move into that space, and consequently you're going to get a bond between one of the chlorines in here. All right, it's going to, oh no, I'm just going to confuse matters by putting that in. But one of those chlorines is going to bond with this radical and produce the chloromethane. And then the other electron that's forming the bond between those two chlorine atoms in the molecule there moves to be a single unpaired electron, so we end up with our chlorine radical. So that's the chain reaction then, that will just keep going. As long as you've got reactants, it'll keep going. But something has to bring it to an end, and actually we then have several possible chain termination reactions. Things that we are potentially left with at the end of this chain that are reactive. Well, methyl radicals and chlorine radicals, basically. The hydrogen chloride over here is not going to react anymore. The chloromethane is not going to react anymore. But we're left with a lot of these and a lot of these. So reactions that will actually terminate this process can occur if two methyl radicals bump into each other, or if two chlorine radicals bump into each other, or if a methyl and a chlorine radical bump into each other as well. That's what we were hoping for, wasn't it? So the termination part of the chain is just about mopping up the free radicals, about taking them out of the picture and completing the process. So the chain termination here, you've got three possible reactions going on. So you could have two chlorine radicals combining, restoring that covalent bond between them, so we end up with those. All right, now they will only stay like that as long as there's no methyl radicals bumping into them or no UV light shining on them. You can have two methyl radicals colliding, and as a result of that you get C2H6, which is ethane. Yes. And then the other option, of course, and the one that we've actually been trying to get all the way through, is that a methyl radical and a chlorine radical will collide, and so we get our CH3Cl, our chloromethane. Okay, so those are the steps in there. Now, it sounds complicated, but actually, when you look at it like that, it's not that difficult. It is just a sequence to follow. And like say for the assignment, you just go through that and replace chlorine with bromine, and you've got it. But it depends, when we're looking at grading, it depends on your explanations, it depends on your diagrams, and it does depend on how far you go, because of course you can continue this to get the CH2Cl2. You can get CHCl3, and you could ultimately get CCl4. Okay, it just depends how much of everything you've got, really, and how long it's happening for, I suppose. So you've got, that's the mechanism, but then, that's the potential for completing it, as it were. It is, sorry? Well, it will, I mean, that will just terminate the production of this. You could, of course, theoretically have, yes, collision between the, what we haven't got is collision between our CH3Cl and chlorine radicals, but that doesn't terminate, of course. That's another chain that you would then get. So this is the simple sort of, that's the mechanism for making CH3Cl. But, you know, in reality, you'd probably end up with a bit of a mixture of those, really, because each one of your completed products, like your your CH3Cl or CH2Cl2, could equally be attacked by another chlorine radical, depending if you've got enough UV light to keep splitting enough chlorine. So it's a matter of how much light there is, how much chlorine you've got to start with, and that sort of thing. So yeah, I mean that's the basic part of it, and then yeah, yeah, really, it's a matter of just yes, yeah. It doesn't it doesn't matter. Enough, assume, just enough to react. You know, I mean, if you've only got you know, one molecule of each, it's it's not even going to happen, is it? You know, so you've got to make the assumption you just have enough. So yeah, don't sort of, you know, you don't have to identify any quantities, but if there was enough material and enough UV light, the process could continue. All right, because that, you know, that initiation there, well, you know, the UV light will break what chlorine there is, but of course at the termination you've got some of the chlorine joining back together again. Now, you know, what's going to split that chlorine? Do you need more UV light? You don't necessarily, because part of the chain reaction will also produce it. So, you know, it's like the chain reaction thing is really important, but at any point in that, conditions could, you know, lead it more towards the termination. So, yeah, it's only explaining the mechanism that I need. I don't need you to actually, you know, consider the conditions particularly. All right, so that's the first one that we're doing. Then that's the free radical substitution. So that's the yeah, that's probably the easier one. I'm not sure really. The other one is electrophilic addition. So I've got another handout stolen mercilessly from Jim Clark, and this one is actually printed double-sided. So this is a little bit more paper friendly. Start at this end. There we go. Okay, again, I've given you the link for Chem Guide there at the top. Okay, so we've got yeah, this comes from his mechanisms bit, and you can see ELADD, electrophilic addition there. What is? This starts off with a nice description of the pi bond, pi system. So this one, electrophilic addition. And the example I think that we're going through on here, I have a feeling, oh yes, it doesn't, it's not a specific one. That's it, yes, all right. The, yeah, it's done on here using XY as a general molecule. So yes, you can substitute whatever seems to be appropriate for X and Y, all right. Yes, I might put hydrogen chloride in there, for example. It starts off then with this idea of the double bond, and electrophilic addition is often going to happen at double bonds. Double bonds are a very specific sort of, well, they're a very common reactive site in organic molecules. So organic molecules that contain carbon-carbon double bonds are going to be very, very vulnerable to this addition process. It's something that's used, I don't know if it counts as this example, but biologically in fatty acids that form part of the fat molecules, the carboxylic acids, you have saturated and unsaturated fats. Yeah. And of course, the saturated ones, well, they used to be bad for us. Of course, now they're not so bad for us, are they? Because people just change their mind. But the unsaturated ones were reckoned to be so much better for our cholesterol levels and all that. And the unsaturated ones contain these carbon-carbon double bonds. So you can have monounsaturates with one double bond, polyunsaturates with more than one double bond. But some of the food manufacturers used to have a bit of a devious way of processing their unsaturated fats, because the problem is the unsaturated ones tend to be oils rather than fats, and they're quite difficult to use, particularly in things like biscuits and that sort of product, where you want I forgot what they call it. Is it the snap in the biscuit, you know, to be crispy? And it's very difficult if you use oil rather than fat. And so what they would do would be to hydrogenate. And if you look on packaging and you see hydrogenated vegetable oil, that's not a good thing, because hydrogenated vegetable oil, well, I don't know, it's an artificial version of a saturated fat, because hydrogen has been added to the double bonds, you see. So that's one of my reasons for doing this, is because it sort of has its applications, really. And yeah, so a hydrogenated vegetable oil hasn't got its double bonds anymore, so it's not unsaturated. It's been saturated with hydrogen, and so it just becomes a more solid product. And so you can actually use it then. I think there's less of that now, but yeah, it's worth looking on packaging anyway. So the idea of electrophilic addition then, so often in unsaturated organic compounds, I didn't really need to write that, but I have, so there we go. All right, and the important bit is this, the idea of the double bond. And double bonds, I mean, we've covered this twice now, I think, already, but I'm going to do it again. Where you've got a bond that's drawn like that, it's not just those two pairs of electrons between the two carbons, not shared equally, just sitting there in between them. What it actually is, we would have to have a couple of other things attached on there. What it actually is your shared pair in between there and there, okay, is our sigma bond. And then the other pair of electrons are found in, well, they could be both of them up there, both of them down there, one up, one down. We have no idea. But that is the pi bond. All right. The dots are surplus to necessity here, but all right, those two, if you remember, those are the sigma bond, whereas these two, this is our pi bond. And the pi bond is a very vulnerable area. Yesterday we were talking about it as a reactive site, because you've got these exposed electrons. So they are going to be open to attack, because they're just sitting there away from the rest of the bond. And so we rely on those yeah, to be our reactive site in this particular example. The example here is using ethene. Now, we didn't spend much time on the unsaturated compounds. I think we got as far as mentioning ethene. And ethene is, if we just took this structure that I've drawn there and we filled it in with hydrogens, then that's ethene. All right, so ethene is C2H4. All right, but our carbons are joined by this double bond, which has the sigma pair and the pi pair as well. And these bonds are very easily attacked by electrophiles. An electrophile, if you remember, you know, I mean, the word means loves electrons. So because you've got these clouds of electron presence above and below the bond. That's, you know, an electrophile can easily approach that area and pull electrons away. You know, it sneaks in and it pulls electrons out of that bond. What happens after that is quite interesting, and that was what we actually started working through on yesterday's curly arrows sheet, which was where it all sort of fizzled out. Right, let's work through the sheet to stop me rambling off in inaccurate directions. Down at the bottom, then there's a definition then of electrophiles attracted to. Oh, an electrophile is something. I might have replaced that with a species, but yeah, something which is attracted to electron-rich regions in other molecules or ions. Okay, and as far as this is concerned, of course, the ethene, our electron-rich region, is going to be the pi bond that's associated with that double bond there. So the electrophile is going to have either a full positive charge or a slight positive charge on it somewhere. Right, the somewhere could mean that it's what sort of molecule? What sort of molecules have a positive charge in one place and a negative somewhere else? Polar, yeah. So typically polar molecules are going to be attracted to pi bonds. But of course, it's going to be the positive bit of the polar molecule that's attracted to the negative electrons, all right, not the negative end. So you need to understand, yes, it'll be the hydrogen. Well done. It'll be the hydrogen end of a molecule that's got, yes, if it's something like hydrogen chloride, hydrogen bromide, even water, you know. So we've got, yeah, to just remember what a polar molecule is. And he's using an example where, well, over the page actually illustrates hydrogen bromide. Remember, polar molecules. All right, so basically the electrons in the pi system are easily attacked by the part of a polar molecule. Right, this is not the only option. That's the important thing to add here. But carrying, it's not going to be a full positive charge. We describe it as delta plus, don't we? All right, the slight positive charge. Okay. So yes, he's done a little diagram of hydrogen bromide. Oh well, let's, for example, not do hydrogen bromide. Let's do hydrogen chloride, which is, yeah, very, very similar. Chlorine, more electronegative than hydrogen, so the pair of electrons is going to spend more time round the chlorine. So we end up with our slight positive charge at that end and a negative charge at that end because the electrons are spending more time around the chlorine. So the hydrogen end of this molecule can quite easily approach the pi system and pull electrons away, and that's really what's going to happen here. Now, in terms of the addition reaction then, what we're going to end up with is two molecules combined into one. All right, so I'm just going to use the ChemGuide example here. We've got the use of a general molecule XY. All right, and I'm going to stick with that. I did wonder whether to change it into AB, and I thought, why bother? So generally speaking, then, addition will result in, all right, our overview of this. We've got our ethane, sorry, it's not ethane, it's ethene. The double bond tells us that. And our, let's say, our polar molecule, XY. And the positive end of that, let's assume that it's going to be the X, I believe. Yes, the X is going to be the positive end. The X is going to approach the double bond, and it's going to pull electrons away and create a bond between itself and the carbon. So we're going to get the X added onto one end. We then have the Y carrying out the remaining reaction with the other end, because we've actually moved an electron pair from the carbon-carbon bond there and used that to bond the X in place. The Y is going to get all the electrons from the bond here, and it's going to use those to react with the other end of this molecule, all right, the ethene molecule. So what we end up with, you can see on the sheet, we get, all right, we've got our, whoops, not really left enough space for hydrogen. We end up with this sort of arrangement where the X is added to one of the carbons and the Y is added to the other. And of course our double bond has gone now, because the electrons that were forming that double bond have been used to create a bond with the X and a bond with the Y. Right, let's have a look at this overall then. I think that's pretty much gone through that second side, to be honest. If we turn to the third side where it says understanding the electrophilic addition mechanism, this is the bit that I want to work through. But as I say, you know, you've only really got to substitute hydrogen bromide for the XY and you're there. However, the explanation is also important. Now, if we start with our polar molecule, all right, and yeah, it's interesting that he's yeah, made the size of those fairly obviously yeah, comparable to something like hydrogen bromide. So if we start with XY, such that we've got a slightly positive charge on there and a slightly negative charge on there, the first thing that's going to happen is that we've got to have this approaching our pi bond the right way round in order to actually have any effect on it. If the let's just consider what the options are. If we've got our ethene molecule here, if our XY comes in, well, the way that it's going to react is that we have XY like that, okay? So that will give us a reaction. If, on the other hand, it comes in with the Y first, all right, it's not going to react because the Y has got the negative charge on it. That end of it is not going to attract the electrons from this bond. So we don't get a reaction there. Similarly, of course, if it came in from the end, it wouldn't really matter which way round, but XY coming in there or XY coming in there, we're not going to get reactions with those either. All right, so no reaction with those approaches, but you do with this one. All right, so as long as the slight positive charge approaches this cloud of electron presence that's forming the pi system, then we're going to get the reaction. Okay, now the diagram in the, well, the second diagram down on that side is, it's got a nice one. It is drawn so that the hydrogens are shown coming out of the page and going back in. If you look, you've got the wedge and the dotted line. I'm not going to do it like that, but the effect is such that here is our carbon with its single bonded sigma pair in the middle. What is drawn on here is a very light sort of impression of, you could find the electrons there, but there's a much greater chance of finding them here. All right, what's actually happening is this bond is being distorted in that direction because you've got your XY approaching that way on. All right, that little positive charge there is pulling the electrons this way. All right, so I don't know how to put that in really. If I just put a red arrow on them, pulling them that way, they are attracted towards the positive end of the XY molecule. Now, this just means that we're just going to be more likely to find our electrons in that part. Okay, nothing has happened yet. If this continues, then the electrons in the pi bond are actually going to come away from the ethene molecule, and they are going to get donated entirely to a bond formed between the carbon and X. So the step that we then have is, actually I've not left any scope here for doing curly arrows, but the step that we've actually got here would be the pair of electrons in here, all right, are going to move there. All right, there's my curly arrow. And what we get as a result of that then is our pair in the middle has gone, so we've only got our single sigma bond there. But we've now got a bond to X as a result. But what's happened to the pair in here is that they are entirely donated to Y. So the X doesn't need them anymore. All right, it's been taken on board over the left-hand side here. And so what we get is our Y now has the electron pair that was originally the bond with X. And because they were sharing a pair, one from each, it's now got an extra one, so it's actually got a negative charge on it. What I haven't considered is what happened here. Because the electrons went from this bond into this, we've now left that with a positive charge. Okay? Because it's lost an electron, you get this positive charge over here. Now, that is a rather strange situation. All right, but it is all fully labelled on this diagram, which is rather nice. The carbon atom acquires a positive charge. Here we've got the electron pair originally used to join Y to X, and negative Y ion formed, and our X atom joined to the carbon using the two electrons from the pi bond. Beautifully described, right? That diagram is very useful to explain what's happened at that point, because that just looks a mess otherwise. What on earth is it? Where have these electrons come from? We have a rather curious name for this thing up here with a positive charge. They used to call this a carbonium ion. They don't call it a carbonium ion anymore. So what do they call it? Yeah, it looks like it says carbocation actually, but yes, to native English speakers it would look like carbocation. Yeah, but it's actually a carbocation. All right, because a cation is a positive ion, isn't it? So it's a carbocation. All right, so carbocation. It's a curious thing that, but yeah, I always look at that and I think carbocation. Yeah, the carbonium ion, older term. But what we've now got, of course, is positive charge here, spare electron there. Well, we can solve that problem. If this is missing an electron and this has got a spare one, well, it's not exactly that difficult then, is it, to move, what was I using, green, to move this pair into here. And what we end up with, I've not taken the traditional three-step approach here, that we've now got X joined onto there by the pair of electrons that was the pi system here, and our Y joined on here by the pair of electrons that was originally joining these together. Okay? Nah. That's it. All right, okay. I remember going to an A-level chemistry training day, and it was about just sort of using activities of various sorts, and they demonstrated various things, including that endothermic reaction we looked at the other week where the temperature dropped really low. And they got us doing activities, and we had to produce an animation, effectively, of this whole process using little ping pong balls and pipe cleaners and pieces of paper and drawing and all that, and using a phone camera mounted in a clamp stand and just taking a picture, then moving the bits, then taking a picture, then moving the bits, and then taking the picture, then moving, and actually then running it together into an animated thing. It took ages, for what you actually got out of it in the end, which was sort of perhaps 10, 20 seconds of these little particles moving about. It must have taken us the best part of, I must have been getting on for an hour to actually make it work properly. You moving the little bits at a time and bringing in labels and all that sort of thing. And it must be great on an A-level course if you've got that much time, studying perhaps 5-6 hours of chemistry a week for 2 years. You can possibly do that. The speed we go at, no, we rely on ChemGuide. You might actually find animations of it online, to be honest, and it's always worth looking because, there are educational benefits from modelling something. It helps you to understand it, probably. And you'll find that that sort of activity has been used, and, the videos will be out there. And, yes, if you get the urge to do your own, well, there you go. That's something to do when it snows you in at the weekend. So you've got the giveaway bit, really, how to write this mechanism in an exam. You've got the curly arrows part of it, which pretty much should match up with what I've done, I hope. Yes, it does, doesn't it? That's a relief. So the first little diagram there, that's the before the actual reaction, where you've got the arrow bringing, all right, his goes out, perhaps more to the left, and perhaps there's a better place than I've put it, so that it does look like it's going to bond the X to the carbon a bit more. I think it's probably a better position. And you've got the pair going from between the X and Y right down to the Y itself. Second diagram shows that this pair that now belong to the Y are donated into the space between it and the carbocation, and you end up with what I've drawn there, pretty much. So, do not leave this page until you're sure you understand how it relates to electron pair movements. All right, so you just got to keep staring at this paper until you understand it. The ChemGuide website's got a lot about the mechanisms on, all right? But although, yesterday it did look like this was going to be phenomenally complicated, I think once you look at these two examples, I don't think they're that bad. Or is it just me? Are they? So they seem okay? Or they just take a little bit of working through, yeah? Okay, we will stop at that point then, and that is the end of the first chemistry unit. So bonding, reactions, and organic chemistry. We've come a long way. We've done an awful lot of content in this. So, you should feel that you have learned a lot. But yeah, where we go from here is another story altogether.